Scientists have discovered something remarkable hiding in plain sight, a cosmic tunnel stretching from our solar system toward distant stars. Using powerful X-ray telescopes, astronomers have mapped a mysterious pathway through space that may connect our corner of the galaxy to regions hundreds of light years away. This discovery challenges our understanding of the space we call home and reveals that our solar system sits in a far stranger neighborhood than previously thought. Researchers at the Max Planck Institute for Extraterrestrial Physics have identified what appears to be an interstellar tunnel, a narrow structure of hot plasma extending from our solar system toward the constellation Centaurus. The discovery was made using data from eROSITA, an advanced X-ray telescope aboard the Spectrum Röntgen Gamma Space Observatory. The findings were published in the peer-reviewed journal Astronomy and Astrophysics. Dr. Michael Young led the team that conducted the analysis, working alongside researchers including astrophysicist Michael Freiberg and Dr. L. Sala. To understand this discovery, we first need to know where we live. Our solar system resides inside a region called the local hot bubble. This unusual pocket of space measures approximately 300 to 1,000 light-years across, depending on the measurement method. Despite its name, the bubble maintains a temperature of around 1 million Kelvin. Before you worry, the atoms in this region are spread so thin that the high temperature doesn't actually heat the objects within it, including Earth. The local hot bubble formed between 10 and 20 million years ago when multiple supernovae exploded in succession. These stellar explosions swept away cold interstellar gas, leaving behind a cavity filled with hot, low-density plasma. The solar system's position near the center of this bubble is purely coincidental. We simply drifted into this region over millions of years. The research team faced a significant challenge. Mapping a structure from the inside is extremely difficult. To solve this problem, they used eROSITA's unique position. The observatory sits about 1.5 million kilometers from Earth at a gravitationally stable point created by the combined pull of Earth and the Sun. This location is crucial because it places eROSITA outside Earth's geocorona, a massive halo of hydrogen that extends over 600,000 kilometers from our planet's surface. The geocorona creates its own X-ray glow when solar particles interact with it, which can interfere with observations of more distant X-ray sources. By observing from beyond this glow, eROSITA provided the clearest view yet of the local hot bubble. The researchers divided the X-ray sky into approximately 2,000 spatial sections. They carefully analyzed the X-ray emissions from each section, comparing eROSITA data with historical observations from the ROSAT satellite, which conducted X-ray surveys in the 1990s. They also integrated neutral hydrogen maps from the HI-4P survey and dust measurements from the Planck satellite. This comprehensive approach allowed the team to separate the faint glow of hot plasma from other sources of X-ray emission. The result was a detailed three-dimensional map of the local hot bubble and its surrounding environment. The map revealed several surprises. First, the bubble is not symmetrical. It expands more strongly perpendicular to the galactic plane than parallel to it. This makes sense. There's less resistance in the vertical direction compared to the horizontal, where more interstellar material exists. Second, the team detected a significant temperature difference between the northern and southern portions of the bubble. The southern galactic hemisphere shows a higher average plasma temperature of 122 electron volts compared to 101 electron volts in the northern hemisphere. This temperature asymmetry suggests that heating events within the bubble were not uniform, possibly because supernovae continued exploding in our neighborhood until just a few million years ago. The most striking discovery was the tunnel itself. The data shows an elongated, low-density structure pointing towards Centaurus. This feature appears to carve through the cooler interstellar medium, creating a pathway of hot plasma extending from our local environment toward more distant regions of the galaxy. According to the research team, this tunnel stands out in stark relief against the surrounding space. It's characterized by low dust content and enhanced X-ray brightness. A similar structure may also extend toward the constellation Canis Major, suggesting these tunnels are not isolated features. The emission patterns strongly anti-correlate with local dust measurements, reinforcing the interpretation that these are genuine large-scale structures with coherent geometry. The researchers also found that the average thermal pressure within the local hot bubble is lower than expected for isolated supernova remnants. This suggests the bubble may be open in certain directions, particularly at higher galactic latitudes, allowing material to flow between different cavities. The idea of interconnected hot bubbles and interstellar tunnels is not new. In 1974, scientists first proposed that space around us might contain a network of connected cavities carved by supernova explosions and stellar winds. However, definitive evidence remained elusive for decades due to limitations in observational technology. These new findings provide significant support for that 50-year-old theory. The tunnels may represent corridors through which cosmic rays travel, gas flows, and dust moves on a galactic scale. They may be the product of ancient stellar winds or supernova-driven shock fronts that carved pathways through the interstellar medium. The discovery matters for several reasons. First, it changes our understanding of the immediate cosmic environment surrounding our solar system. Space between stars is not uniform emptiness, but a complex landscape shaped by violent events over millions of years. Second, these structures may influence fundamental processes in our galactic neighborhood. The tunnels could influence the distribution of cosmic rays that occasionally strike Earth's atmosphere. They might influence how interstellar gas and dust move through our region of the galaxy. Understanding these pathways could help explain patterns in stellar formation and the chemical composition of nearby space. Third, if these tunnels are part of a larger galactic network, as the 1974 theory proposed, they may connect multiple star-forming regions and hot bubbles throughout our arm of the Milky Way. The researchers suggest that what they've discovered might just be a small piece of an extensive system of interconnected cavities. The tunnel towards Centaurus may connect to several features in that direction, including the Gum Nebula and various molecular clouds. Another neighboring bubble of hot plasma also lies in that general direction. Whether these features are all connected remains an open question. Scientists emphasize that much work remains. Not every aspect of these structures is understood. Some sightlines appear to be supported by linked cavities, while other regions seem more blocked. The complexity of these patterns will require more sensitive instruments and further analysis. The discovery of an interstellar tunnel connecting our solar system to distant stars reminds us that even our own cosmic neighborhood holds surprises. As new X-ray missions launch and mapping techniques improve, astronomers expect to fill in more details of this hidden network. What once seemed like empty space between stars now appears to be a dynamic, interconnected landscape shaped by the violent deaths of ancient stars. Our place in the cosmos may be stranger and more connected than we ever imagined.